Good morning or whatever time it is. Welcome again to Humpkey's Study. What is it, Quill? I didn't get that. Gotta listen better. Oh, Quill says you should tell him about the chickens. Oh, well, yes, the chickens. The little chicks are outside. I put up a little video or a link to a video, and you can see the chicks in their new environment. We only have 4 left. Out of the 18, they've all been distributed. One unfortunately didn't make it, but all the rest of them are just fine, and they all have their regular feathers on now, and about 3/4 grown. So have a look at that. We have to do some linear algebra though, you guys. Yeah, okay. See you soon. All right. So today I thought I'd talk just a little bit more about this change of basis. Talk about what it can do, what it can't do maybe. So here I give you 2 equations or sets of vectors, both given as linear combinations. This is the kind of thing you would get if you solved a system of linear equations. You might get such a solution. And both of them are planes. The first one is in 4-dimensional space because these vectors are 4-dimensional space. This is a linear combination of 2 linearly independent vectors. They're not multiples of each other. The second one is also all linear combinations, free variables of linearly independent vectors. So this is also a plane, but this one lies in 3 space. So we can do some problems with these. So for example, find a basis for P2, or find a basis for P1. So a basis for P2, in order to find a basis, you want to write P2 as the span of some vectors, of a collection of vectors. And if these vectors are linearly independent, and if P2 is the span of them, then it's a basis. The dimension of these is 2, so we need 2 vectors. And for this one, the vectors that it is the span of in the solution notation are linearly independent. So P2 is the span of these 2. So a basis for P2 is simply those 2 vectors. So that's in general how you handle a basis problem. It's not always so easy. Sometimes you have to reduce the collection to a collection of linearly independent vectors. In this case, they obviously are. I could also say find a stepped basis for P2. And to do that, you can begin with any basis and use method 1 from the book. So we want to put these vectors in the rows of a matrix. Get reduced row echelon form. I guess we don't need Mathematica on this. Minus 2 times row 1 added to row 2. Using the idea that these elementary row operations are linear combinations, so the rows remain in P2 and remain linearly independent. So the first one remains the same. 0 minus 2 times this plus this is 1, minus 2 times this is 2, plus 1 is 3. And now then the stepped basis, let's call this basis B2, and the stepped basis is 1, 0, minus 1, 0, 1, 3. And let's call this B2S. Stepped basis derived from basis B2. And finding a stepped basis is always this easy. You can always tell if a basis is a stepped basis by putting these in the rows of a matrix, first row, second row, and so on. And if the matrix is in reduced row echelon form, then it's a stepped basis. Okay, now the next question is change the basis. Find change of matrices, change of basis matrices from, say, the subspace P2 with basis B2 to P2 with basis B2S. So find this change of basis matrix from here to here. So I think we've got enough space to do that, or at least to tell you how to do it. So what you want to do is the matrix consists of, well, let's write a blob diagram here. Even though these are planes, I'm going to call this P with basis B2. And over here, P with basis B2S. So take each one of these basis vectors one at a time, write them in terms of the basis B2S, and we'll see what we get. So that's what we're going to do. And so the first basis vector from B2, this is 1, 0 according to B2. And 1, 0 means the first basis vector. So if we write it in standard notation, it's 1, 0, minus 1. And then we want to write this as a linear combination, A times the first one of this. Were these the same? Yeah, I guess this is the same. Plus B times the second one, 0, 1, 3. Now, the nice thing about the stepped basis is when you do the arithmetic on the right-hand side, you get 1, 0, minus 1 equals, when you add these guys up on this side, you get A plus 0B. So the first one here will be A because this is a stepped basis. And because it's a stepped basis, when you add the second coordinates up, you get B. And then the third coordinate is minus A plus 3B. But the first two tell you what A and B are. A is 0, A is 1, B is 0. So A is 1, B is 0. And that is the first column of T. So taking the first one of B2, writing it in terms of B3, you get 1 and 0. And now to get the other column, we take 0, 1 according to B2 and write it in terms of the stepped basis, B2S. So 0, 1. Give myself maybe a little more room. Take 0, 1 according to B2. This is 0, 1, 3. The second, no, this is 2, 1, 1. The second basis vector from B2, none of the first, one of the second, just means the second. So this is standard notation, but in 3 dimensions. And you want to write that as something times 1, 0, minus 1, plus something else times 0, 1, 3. And the A and the B are what are going to go into the columns of this matrix. And if you write this out, you get A, B, and minus A plus 3B. But this time, A is 2 and B is 1. So A is 2 and B is 1. So here is the matrix that transforms the basis B2 to the basis B2S. Any questions about this? Sky? No? Okay, so then from the other direction is T inverse. You can find T inverse if you want using Mathematica, but T inverse goes from B2S to B2. The other one works basically the same as this one. Okay. Change of basis matrices on subspaces of these two. One other thing I'd like to show you is that there's a nice correspondence between P with any basis. Let's say, let's take P1 this time with basis B1. There's a nice correspondence between there and the normal plane with the standard basis. Now, this is not change of basis, but this is just a relationship between these two. So I'll call this F, just to tell you what the relationship is. And the relationship is really this, that if you take F of any basis element, like 1, 0, according to B1, this will be equal to 1, 0, according to the standard basis in R2. So this means something in the plane, in this case, a plane in four-dimensional space. F of 0, 1, according to the basis B1, is going to be 0, 1, according to the standard basis in R2. So this is all happening in the plane P1, and this is all happening in the standard plane R2. Now, P is not equal to R2. P1 is not equal to R2. R2 is a standalone plane. This is a plane that happens to be embedded in R4. But this relationship, the matrix representation for F, the matrix representing F then, is the identity matrix. Now, this doesn't mean things are identical. This just means that if you use the basis B1, that the structure of this plane is the same as the structure here. The reason this isn't change of basis is that these lie in different positions. So this is not something, this is something that I am wanting to be equal, or I'm setting equal. But once you do, this tells you that the structure of those two planes is identical. So I gave you a bunch of problems where they all have to do with changing bases from one space with its basis to another space with its basis. Column spaces, row spaces, or if I give you linear transformations, kernels and ranges. And these problems, and there are a pile of them, but they're all pretty quick, and they help you keep this stuff straight. In any case, thanks a lot, and see you Monday.